First of all, thank you very much to the organizers for the opportunity to speak, and thank to all of you for being here at 5 p.m. on Friday. So the talk will be about a notion of two-stack over a two-dimensional grothic site that I introduced as part of my PhD project. I will first recall the notion of stack, then we will move to the notion of two-stack, and we will end by seeing the motivating example of quotient two stacks. Okay, so if we have a category C with pullbacks, a sieve on an object C of the category is a collection of morphisms of codomain C that is closed under precomposition, or equivalently a subfunctor of Yoneda of C. And if we have sieves, we can define grothic topology as an assignment for every object of C of a collection of sieves that we call covering sieves, in a way that the maximal sieve is a covering sieve, it is closed under pullbacks, and the third condition just says that being a covering sieve can be checked locally, where locally means with respect to another grothic sieve, covering sieve. So now we want to introduce the notion of stack, and when we speak about stack, we have to think of a two-dimensional sheaf. So it is a pseudo-functor that is still able to glue together local data into global data, but this time the global data only recovers the local data up to isomorphism and not on the nodes. So the notion of local data that we want to have in mind is that of a descent datum. So if we have a pseudo-functor F and a covering sieve on an object C, a descent datum on S for F assigns to every object in the category, to every morphism in the sieve, so F from D to C, an object in the image of the domain of the morphism, so this WF. And then for every pair of composable morphisms, like these ones where the second one is in the sieve, we get an isomorphism phi Fg between the assignment on the composite of F and G and the descent along G of the assignment on F. And these isomorphisms are coherent in the sense that if we now take a chain of three morphisms, we get a commutative diagram relating all the different isomorphisms that we get. And this commutative diagram is called the cocycle condition. And we say that this descent datum is effective if we can find an object that now is a global object, so in the image of C, such that for every morphism in the sieve, W of F, so the assignment on F, is isomorphic to F star W. So the idea is that this global object W allows to recover all the local objects up to isomorphism. And these isomorphisms need to be compatible with respect to composition as well. And so now we can say that a pseudo-functor F is a stack if every descent datum for it on a covering sieve is effective. And additionally, we have a condition of gluings on morphisms. And this says that if we now have if we fix two objects, X and Y in F of C, and we have a bunch of morphisms between F star X and F star Y for every F in the sieve, and these morphisms are compatible, we can glue them together into a global morphism from X to Y that recovers all the local ones, this time on the nodes. And the idea is that this is a sheaf condition. This is saying that every matching family of morphisms has a unique amalgamation. But there is also another way to think of a stack, and the characterization is due to Strict, is actually the definition that Strict uses. And so F is a stack if and only if for every covering sieve S, the functor of precomposition with S is an equivalence of categories. And the idea behind this characterization is that this category on the right is the category of descent data, and the conditions of equivalence of categories are effectiveness conditions for these descent data. Let's see more in details, because it will be useful for when we speak about two stacks. So, first of all, we notice that here on the left, the black category is equivalent to f of c by the two-categorical version of the Yoneda lemma. And we will call gamma the equivalence given by the Yoneda lemma. And so now, if we take an object of the blue category, this is a pseudo-natural transformation from R to F. And so for every object of D, we have a functor like this. And this functor sends a morphism F into an object of F of D. And this is exactly the assignment of the descent data, because we are saying that this alpha is actually a descent data. And then if we have a morphism G, the pseudo-naturality of alpha gives a pseudo-natural transformation alpha G, whose component on F is exactly what we called phi Fg before. And then the fact that this is pseudo-natural actually gives the cocycle condition as well. So this is exactly the descent datum, and the fact that this alpha needs to be isomorphic to the image of a certain W is exactly saying that the descent datum is effective. And if we now look at the fully faithfulness of this composite of functors, we get that if we fix two objects in f of c, a modification, so a morphism in the blue category, is just given by a bunch of natural transformations, and the component on f is a morphism between f star x and f star y. And again, we recover the condition that we have on morphisms, so the fact that we have a sheaf condition on morphisms. Okay, so now we are ready to move to dimension 2. So now we take K, a small 2 category, and we want to endow it with a two-dimensional version of topology, and the one that we consider is the one that Street introduces for bicategories. So a bi-sieve over an object C is a fully faithful arrow into unit of C. And so we can make some comments about this definition. So first of all, we are not asking in the definition that S is injective on objects. But every time that we take a bi-sieve, there is another bi-sieve equivalent to this one that is actually injective on objects. And all the properties that we want to study are invariant under equivalence, and so we will consider only bi-sieves that are injective on objects. And this is good because this allows us to speak of morphisms in the bi-sieve. Second comment is that now S is a pseudo-natural transformation, and so the bi-sieve is closed under precomposition only up to isomorphism. And the third comment is that since S is full, we are actually taking all two cells in every sieve. So we are not choosing two cells. And now a bitopology on the two category K assigns to every object in the two category a collection of covering bi-sieves, and the axioms that we want are analogous to the one that we have in dimension 1. The only difference is that now we upgrade pullbacks to bi-isochroma objects, so bi-dimensional pullbacks. And so now we have that the bitopology is closed under bi-isochroma objects. Okay, and now we can try to naturally generalize the characterization of, yes?
I'm sorry to interrupt. The prefix bi here refers to a bi-categorical limit. Is that
I call it bitopology because Street introduced it for a bi-category. I'm only considering the case if K a 2 category, but this is actually more general. Okay, so now we can naturally generalize the characterization of stack given by Street, and we can say that a triomomorphism from K up to B cap is a 2 stack if for every covering by sieve, the pseudo-functor of precomposition with the covering by sieve is a bi-equivalence. And this is a very natural thing to do, and is completely analogous to what is done in the context of other higher dimensional stacks, for example, infinity one stacks. So this is a natural and nice definition, but the problem with it is that it's very implicit. So if I now want to prove that something is a two-stack using this definition, this is going to be painful, because I have to deal with a lot of free categorical coherencies and things like that. So what I wanted to do is I wanted to find explicit conditions, like the one of stacks, that we want to prove, to say that something is a two-stack. And the idea to do this is exactly the idea of the proof of the characterization of a stack. So we'll need to use the Yoneda lemma again, and we do have a Yoneda lemma for three categories, and this is due to Bounet, and it works exactly like the Yoneda lemma that we all know. And moreover, we are going to use the fact that bi-equivalence means surjective on equivalence classes of objects, essentially surjective on morphisms, and fully faithful on two cells. And so we will find the right gluing conditions on objects, morphisms, and two cells using this fact. So let's start from the objects. So now the idea is that an object of the bi-category here in blue should be some kind of descent datum on object. But what we expect to find is actually something weaker than what we were used to have. So an object here in the blue bi-category is a tree transformation from R to F. And so this is given by a bunch of pseudo-functors, again, one for every object of K. And these pseudo-functors, as it happened for the stacks, send every morphism in S to an object in F in the image of the domain of the morphism. So we still have a bunch of objects like this. But we also have an assignment on two cells. So if we have a two cell from F to F prime, we get a morphism from WF and WF prime. And this is simply because we are considering a two-dimensional sieve. So we need to have an assignment on two cells. And then we also have, for every morphism G, a pseudo-natural transformation alpha G. And if we now compute the component, consider the component on F of this pseudo-natural transformation, this is going to be an equivalence and not an isomorphism anymore. But this equivalence still relates the same kind of objects, with the only difference that here we don't have an assignment on the composite of F composed with G in general, because the bi-sieve is not closed under precomposition. So here F composed with G tilde means a morphism isomorphic to F composed with G, which is actually in the bi-sieve. And then what we get, among other things, is a bunch of invertible modifications, one for every pair H and G of composable morphisms. And a component on F of this invertible modification is an invertible two cell like this. And the idea is that this is a weak version of the cocycle condition. So the cocycle condition is not a commutative diagram anymore. It is instead a coherent two cell. And of course we have a lot of other coherencies, for example, compatibility with respect to composition and of two cells of morphisms and a lot of other things. But the idea is that we know what these coherencies are because we know what a tree transformation is. And so we call this object a weak descent datum both because the cocycle condition is weaker and because here we have an equivalence instead of an isomorphism. And now, looking at surjectivity and equivalence classes of objects, we discover that alpha is equivalent to the image of a certain object W in f of c, exactly when we can get a tree modification like this, and the component on f of this tree modification gives an equivalence between WF and F star W. And this is a weak version of the effectiveness condition that we might expect to find. And now if we look at what happens on morphisms, what we expect to find is that every descent datum on morphisms is effective, and this is exactly what we find. So if we now fix x and y in f of c, and we take a morphism in this bicategory, we get a tree modification between the image of x and the image of y. And so this is given by a bunch of pseudo-natural transformations, and the components are exactly morphisms between f star x and f star y. And of course, we also have an assignment on two cells as well. And then, given a morphism G, we get an invertible modification whose components are exactly isomorphisms phi f g, relating G star WF and WF composed with G tilde. And the axioms of tree modification actually give the cocycle condition on morphisms. And now the essential surjectivity says that this descent datum needs to be effective. And then when we look at two cells, what we expect to find is a sheaf condition this time, and we do find it. So if we fix two morphisms A and B from x to y, and we look at the perturbation between the image of A and the image of y, what we get is a bunch of modifications whose components are two cells between f star A and f star B. We get all the compatibility conditions that we want, and the fully faithfulness is exactly the condition that P is the image of a certain two cell W, and this is exactly saying that WF is equal to F star W for every F. And so, summarizing, what we get is that a triomomorphism is a two-stack if and only if every weak descent datum, in the sense that we saw before, is weakly effective, every descent datum on morphisms is effective, and every matching family of two cells has a unique amalgamation. And we are happy with these conditions because they are the conditions that we expected to find, but also we couldn't have given the definition of two-stack directly in this form, because we didn't know what the right coherences, we didn't know the right coherences to ask for weak descent data. So the idea is that the implicit condition guides us in finding the right coherences to ask. And now I'm going to tell you why I care about this notion of two-stack. So the main idea of my PhD thesis was to generalize principal bundles and quotient stacks to categorical contexts. So I did this for the context of a one-dimensional site, and then I wanted to do the same for a context of a two-dimensional site. And is there a question? No. And then when I got a higher dimensional version of what should be a quotient stack, but the thing is that there was no notion of higher stack suitable for that kind of triomomorphism. And that's why I decided to introduce this notion. But let's do a step back. So what is a principal two bundle? So if now K is a small 2-1 category with isochroma objects, actually I can give this definition for a two category, but to construct the quotient stack I need a 2-1 category, so I'm taking this hypothesis early. The idea is that we can define what a locally trivial morphism in the two category is using the covering bisieves. And then we are going to say that a principal 2 bundle is just a G equivariant to locally trivial morphism of this kind. And with this kind of principal 2 bundles, we can construct quotient free 2 stacks, and given fixing an object X, we send every object Y in the 2 category of principal G2 bundles over Y, equipped with a fixed equivariant morphism into X. And then we define the assignment of morphisms via isocomma object, and the assignment of 2 cells via the universal property of the isocomma object. And why do we care about this kind of stacks? The reason is that if X is the terminal object of the category, this is a classifying stack. And so it has relations to the calculus of cohomology. So we want to do this because of cohomology, essentially. And I had this object, and I managed to prove that under mild assumptions on the 2-1 category, this is a 2 stack. And these assumptions are exactly the same that I had in dimension 1 for the quotient stack. And there were many ideas behind the proof, but one of the most important ones is that so here we are taking a subcanonical bitopology, and we know that in dimension 1, every element of a subcanonical site can be seen as a co-limit of every covering by C over it. And I managed to prove a similar result in dimension 2, where this time the co-limit is actually a sigma bicolimit, so it is a Laplace-Mark co-limit. But still we can see every object as a kind of higher dimensional co-limit of the pi sieves over it. And this is what allows us to prove that X over G is a 2 stack. Here are some references, and thank you very much.
Away from the color coding, because it's hard work, and you do a very good job of making it understandable. Questions? Please.
I've got lots of questions. I'll only give you one. Thank you very much. So if you've got I think you're describing a geometric stack in terms of G bundles. There's normally like a standard characterization of geometric stacks in terms of having representable diagonal significant company. I was just wondering if you covered that.
Yeah, not yet. So this should be a geometric 2 stack, but there is no notion of geometric 2 stack yet. So I plan to introduce one and prove that this is a geometric 2 stack indeed.
Thank you.
Other questions? Yes, sorry, Thanks
for the talk, Elena. Yeah, I'm glad to see that you're now referring to this thing as a classifying stack, which sort of related to my question the last time you presented this material when it was in an earlier phase. So could I ask, can you explain more what this classifying property is for your quotient stack?
So the classifying stack should classify principal bundles.
Mm-hmm.
That's what it does. So these higher classifying 2 classifying stack should classify 2-dimensional principal bundles.
So you say it should? Do you have like a...
I haven't looked at it yet.
Okay.
Other questions? Yes, please.
Maybe a question. Is there any simple example for the bitopology or the bisite?
So the main examples I think come from internal categories into a category. So, for example, the principal 2 bundles have been used in mathematical physics mostly. The principal 2 bundles, so these ones, for the category of categories internal into manifolds.
Mm-hmm.
So this is an example.
Clemens.
When you have a two-stack, is it possible to define in a canonical way an ordinary stack by somehow caution out everything from that dimension two?
That's a good question. I don't know. I haven't thought about it. It might be possible. Actually, when I started looking at the principal two bundles, I thought there was a notion of two-stack suitable for the thing that I was getting. But so I didn't plan to introduce a new one, but there wasn't. So I haven't really studied this notion yet because the project was a bit different. But I plan to do it in the future.
Yes.
Yeah, I have two basic questions. How does this notion relate to kind of the existing ones of higher stacks? So like we have, I don't know, differential stacks or infinity stacks already deal with this higher something. Depends on kind of which side you're looking at for the functor, but yeah.
Yeah, so the thing is that the notions are similar, but they are for different kind of triomorphisms. So for example, if I take the notion of infinity stack, and I truncate to get a two-stack, here the two-stack only takes values in 2-1 categories. So that's why it is not suitable for my purposes. And then there was another notion of two-stack, which takes values in really by cat, but this one was by Campbell, but the domain was only a 1 category. So again, it was not good for my purposes.
Inadequate. Okay, cool, thank you.
Okay, to allow time for changeover, I think we better thank Elena again.